All right, everybody. So we are going to be looking at different types of chemical reactions today, and we're going to be starting here. So when we're talking about chemical reactions, there's always going to be energy involved. So that's either energy to break bonds or energy to build bonds. So we can see energy being involved in a reaction in two different ways, but the big thing to remember is that there's always going to be energy involved. So you just want to make sure that you are filling out your notes so they correspond with these slides. So when we look at how chemical reactions are classified, we look at how the energy is comparing for the reactants and the products. So is the energy of the reactants higher than the products, or is the energy of the reactants lower than the products? So we're basically seeing, is the energy decreasing in the reaction, or is it increasing in the reaction? And there are two definitely different types. So what we end up seeing here, this is an example of how you would burn fossil fuel. So this is how things work in an internal combustion engine. You have this fuel combining with the oxygen in the air. So this is combustion when you have fuel burning with oxygen. And what that causes is the breaking down of the bonds in the fossil fuel. And when those bonds are broken, we get a ton of energy released. And this is really important when we're talking about combustion and using this in an engine, because if we wouldn't have the energy from this reaction, cars would not move anywhere. So this is why we need gasoline for an engine. And we also see the same thing here when we're trying to create something like glucose from carbon dioxide and water. So this is how plants photosynthesize. They require energy to build these bonds. So this is where we see the energy coming into the reaction to build the bonds. Okay, so it's a little bit different, and these are two examples of two different types of reactions. The one type of reaction we see a lot is an exothermic reaction. And if we think back to bio, where we have a lot of Greek and Latin roots, exo means out and thermic means heat. So this is where the heat is being released. So this is where we're forming new bonds, and that creation of those new bonds releases a lot of energy. So here, the energy released is greater than the energy used, or the energy used is less than the energy released, okay? So this is where heat is being released. So fire is a great example of this. You're breaking a ton of bonds, and all that energy being released is why fires are so hot and so bright, all different forms of energy. And some examples we see with that is oxygen reacting with hydrogen to create water. So this is the synthesis of water, and from this we get a ton of energy. And this is actually quite interesting. Once this energy is created, that's enough energy to propel the next reaction, which propels the next reaction. So we end up having a domino effect. On the other side of that, we have endothermic reactions. So if we think about those prefixes, thermic still means heat, and endo means in. So this is where heat is going into the reaction. So this is where you see the energy used being greater than the energy released, or on the other side, the energy released is less than the energy used. So this is where things get cold. So some examples of endothermic reactions are photosynthesis, where you have energy coming into the reaction to form these new bonds. And when that energy comes in, that means it feels cold. So let's say you have an endothermic reaction that you're holding in your hand. That heat, that energy that's required is getting pulled out of your skin, which is why you feel it getting colder. Your hand is getting colder because it's losing heat. So that's an endothermic reaction. And when we see the two, exothermic is where the heat is transferred to the surroundings. Endothermic is where it's transferred from the surroundings. Exothermic, we see a rise in temperature. Endothermic, we see a fall in temperature. So there's just the difference between those two. And activation energy is that first initial spark of energy that we need to start a reaction. So in the activation energy, we're going to be seeing some graphs coming up next, and I'll show you where you can see that on these energy diagrams. So here you have the reaction of combining hydrogen gas and oxygen gas to create water, and energy is released, meaning this is exothermic. So here, this little bump in the graph, that's what we call activation energy. And that's the energy that we need to go up and break the bonds and then reform the bonds. So that's just what we call it and where we see it on the graph. So when we look at a flammable material, it is impossible to get that to start on fire without having some kind of a spark. That spark is that activation energy. So this is why you're always told to never talk on your phone while you're pumping gas. That's because those fumes in the air around you can get easily ignited with that activation energy from a single spark. And that causes a chain reaction to then have something explode. When we look at some endothermic reactions, a lot of these are very useful. We see these often, especially this is a huge example, and you've used it before, is an ice pack. So in an ice pack, you crack open this sealed water, and when that comes in contact with ammonium nitrate, it absorbs heat from its surroundings or causes an endothermic reaction. So it feels extremely cold. And once that reaction is finished, you notice that an ice pack will eventually warm up and stop being cold. That's because the reaction is over. So that's what the reaction looks like if you're looking at it, but we don't really need to worry about that too much. We're just looking at some simple examples right now. And so this is where we see a general energy diagram, and you're going to end up seeing this when we're in lab looking at the temperatures of different reactions. Here you have an exothermic reaction where the reactants go up in energy, and then that heat is being released here in this huge slope down, and the products are lower in energy than the reactants. So we lose energy as far as an exothermic reaction. Whereas an endothermic reaction, the reactants go up, 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 and the products have a higher energy because that heat has been absorbed, okay? So here, the reactants are lower than the products. So just remember, here we have the reactants going down to products. Here we have the reactants going up in energy to products.
Please call the main office.
Sorry for that interruption. So we can also look at things like catalysts. You may remember from biology, a catalyst is used in a bodily reaction, but this is essentially, it lowers the amount of energy you need to start a reaction. So catalysts just make things go a little bit faster and are actually quite useful in biology. So when we're looking at here, I want you to try to figure out, is this endothermic or is this exothermic? And is the activation energy high or low? So pause the video and try to figure it out. Okay, so you paused it. So this is a very endothermic reaction. The reactants are much lower in energy than the products, and we have a huge activation energy. Look at this big jump that has to happen in order for this reaction to work. This is huge. This is a ton of energy here. For the next one, oh my goodness, sorry for the interruption. So is this one endothermic or exothermic? And also, does it have a high activation energy or a low activation energy? So pause the video and try to figure it out. This has a very exothermic reaction. Look at how the reactants are losing energy, and then we have a very small activation energy. So it does not take a whole lot of energy for this reaction to work, and we see all this heat being released here. Is this problem an endothermic or exothermic reaction? And does it have a high activation energy or a low activation energy? So pause the video. This is an endothermic reaction. So we see here the reactants are still lower in energy than the products, but our activation energy is not quite as high as that last one we saw, okay? So it's not as big of a jump. So this is the end of this program. Hopefully you got what you needed from it. Please feel free to rewatch this and make sure that you get your notes completely filled out. I would definitely make sure that you have these slides done with these answers, because you are going to be expected to know how to read one of these graphs and how to figure out if something is exothermic, which looks like this, where the reactants are higher than the products, or an endothermic reaction. An endothermic reaction, where the reactants are lower in energy than the products, okay?